Momentum. Morning, kids. Could you say that louder? Get you on microphone there, McKean. I don't know if you heard that at home, folks, but she does not want to learn. My advice to you is to go to sleep then. You can always watch this video later. Today we're going to talk about the conservation of momentum. I might have spelled it wrong. Who knows? This looks like a Mew. What? That? Well, if you think your handwriting is so wonderful, you get up here and do this. Total momentum of a system is the same before and after what we call an inelastic collision. Oops. An elastic collision. Total momentum of a system is the same before and after the collision, an elastic collision. So, what would be an example of an inelastic or an elastic collision? Imagine, say, two of our carts. Remember those carts that we did the motion detectors on before? If we were to take two, have their magnetic ends pointing at each other so that they wouldn't actually touch, but their north poles would repel one another, and they would get close and then stop and then go back. The total momentum of the system would be the same before and after that kind of a collision. It doesn't always have to be just a collision. It'll work lots of different kinds of examples and problems where all sorts of things happen, but if you want to articulate this as a formula, it's real simple. It's the total momentum before equals the total momentum after the collision, which is an awfully simple way to put it. So, what does this mean? Well, we need to maybe focus on one example. Let's look at an example of two vehicles, and not vehicles, let's say, just have two carts. Let's have two carts. Let's have a cart that has a mass of 5 kilograms, and another cart that has a mass of 2 kilograms. And let's consider that before, in our before picture, this 2 kilogram cart is motionless with respect to the Earth. And let's say that this cart has an initial velocity of 5 meters per second in the direction of the other cart. Now let's consider that maybe there's some sort of Velcro or something on here so that when the two carts collide, in this particular example, what we're going to have them do is they're going to stick together. Maybe there's tape or Velcro or something on them so that whenever this one, which is moving, hits this one, which is not moving, they will stick together. Now, without getting into the math or the conservation of momentum or anything at all like that, just intuitively, what is your guess as to what will happen after assuming they stick together, what will happen then? They will what? They will, you said, so someone pointed to the right. Someone said slow down together, so they're going to stay together because they're going to stick. And so they will, will they continue moving? Will they move, and they'll continue moving to the right, and with what kind of a velocity? Will it be more, less, or the same? Less, more, the same, same. So what is the so we can use this conservation law to solve this problem. Here we have the momentum total before the system. What is the total momentum of the system before? Well, we got to be careful because there are two different objects. There's object A and there's object B, right? So to get the total momentum of the system before, we need to add those up. So the momentum of A before, so if we rewrite our conservation formula, it becomes like this. The total is actually equal to the momentum of A plus the momentum of B before, and that's going to equal the momentum afterwards of A and B. Now notice afterwards I didn't write momentum of A plus momentum of B, I wrote momentum of A plus B, and the reason I did that was because in this problem they're going to stick together, and so we're going to treat them as one object. The two become one here. So we can start plugging in what we know. Then what is the momentum of object A before the collision here? It's 25. It's 5 times 5. And the momentum of object B before the collision? 0. And the momentum of A and B after the collision, we now know is, according to what I just wrote on the board, 25, isn't it? So before the total, 25 plus 0, after the total has to be 25. So the momentum of A and B together after the collision is 25 Newton seconds. I tend to write momentum in terms of Newton seconds instead of kilogram meter per second because it's faster to say and faster to write. So momentum of A and B. Now that was not the question. The question was, how is it going to be moving? What will its velocity be after? So what will the velocity be after? Well, afterwards we got to be careful because now the momentum is actually, it's not 5 or anything, it's the 5 plus the two different masses added together, times the new velocity, which is what we're trying to find out, is equal to 25. So we got the mass of A plus the mass of B, mass of A plus mass of B times 7. Or times V is equal to 25. So now we can, to find the velocity, we can simply take 25 over 7, which is 3 4/7, which is some number. And 3, what's 4/7? It's a 0.58, I don't know, 5/7, 5/7. And that unit is meters per second. So we just found that this object, let's go back to the original question. I asked, will it continue, will it slow down, will it speed up, same speed? You guys, at least one of you guessed it slowed down. Turned out that you were correct because it started at 5, and afterwards the two together is 3.6. Well, what's responsible for this? Well, what's responsible for this is that you did have something going fast, but it had a smaller mass than the thing that was moving at the end. At the end, you had something with a mass of 7 moving, so its momentum, if it's going to be the same, had to have a smaller velocity to compensate for that. And so that's the first real simple classic example of a collision in conservation of momentum.